welcome to our presentation of missing value imputation with MERCS, a faster alternative to MissForest. So the problem setting starts with looking at what a typical machine learning model can do. So given a table with 3 columns, the typical setting for a machine learning model is very strict. Given X, so in this case column 1 and column 2, or the values of column 1 and column 2, what's the value of the third column, what's the value of Y. So for a single instance, this means given the value for this attribute, given the value for this attribute, predict the value of the third attribute. So this is like the archetype machine learning setting, which has an obvious disadvantage that it's like a very idealized scenario. Like if you do not know the exact task on beforehand, this table-like paradigm of clearly separated input and output attributes essentially breaks down. So we want to make this more general in a sense. So let's first define what we mean. So when we say we want to be robust to missing values, this means, in the context of our paper, that we want to be able to solve a prediction task like this. So using the same graphical language as before, given the values for the green columns, or for the green attributes, what's the value of the red attribute? So for the first instance, nothing changes. Still, given the value of the first attribute and the value of the second attribute, I want you to predict the value of the third attribute. So nothing changed here. However, in the second row, you are only given the value for the first attribute. The value of the second attribute is missing, but you don't care. And you still want to predict the value of the third attribute. So basically, missing values are present in your dataset, but you still want to be able to predict the last column regardless of the presence of the missing values. So that's what we mean when we say we want to be robust to missing values. Practical example is, for instance, machine learning in industrial context. This often depends on sensor data, for instance, in an anomaly detection application. And so whenever a single sensor breaks down, we do want the AI system to be able to carry on and perform as well as possible, although less input information is available. So this practical situation basically maps to, well, exactly the kind of problem that we illustrated before. So at the second timestamp, it would mean that sensor 1 still works, but sensor 2 is just not giving any reading, but you still want to predict whatever quantity it is you care about. So you don't want the system to break down because here at this time point, sensor 2 breaks down. Another example would be, for instance, autocompletion in spreadsheets or a web form. So you want to be able to do your autocompletion of certain cells, even if the user doesn't fill in all the other cells yet. So again, here the user may have filled in the city that he or she lives, but has not yet said which street he or she lives in. But regardless, you want to make a suggestion of this value right here. So again, it maps completely to this setting that we said before. So this is again an example of a practical situation where you would actually like to be robust to missing values. There's other approaches to solve this problem. So first and foremost, there's naive imputation, as we call it in the paper, which is basically guess the missing values and substitute a fixed value such as the mean or the median, and then carry on as if nothing was ever missing. Secondly, the most rigorous approach, I would argue, is probabilistic graphical models. So that means that you use probabilistic inference to infer the most likely values for the missing entries based on the known ones. And then thirdly, iterative approaches, which are very popular, is, well, the problem is then given a dataset with missing values, you fix the missing values in a single column, you retrain your model using your recently fixed values as inputs in this retraining step, and then you repeat this until you fixed all your columns. So that's the iterative part in the iterative approaches. And then lastly, what we propose is to use MERCS. So that's a multi-directional model, which I will come to in a bit. You need to train it once, and then you use it to predict any column. So that's the main difference that we're trying to exploit here, is that iterative approaches need to retrain, and MERCS would differentiate itself because it only needs one training step. So this identifies the gap in knowledge, is basically the fact that, well, naive imputation is fast but inaccurate. Probabilistic graphical models are slow but pretty accurate. I mean, probabilistic inference is rather expensive. But then iterative approaches, they're accurate, but you need this retraining step for each instance that comes in, which you want to avoid. And that's where MERCS would come in. So it's a possible alternative for these iterative approaches. In a sense, it's pretty similar to what they do, but MERCS would avoid this retraining step, which would make it particularly applicable to the context, to the problem setting that we just explained. So to summarize, the first research question is, well, can we make a MERCS model robust to missing values at prediction time? And then secondly, how does MERCS compare against MissForest? So our first research question is how to extend the MERCS framework. So can a MERCS model be made robust to missing values at prediction time? First, I should tell you what a MERCS model is. So if this is a classical unidirectional machine learning model, and from the first two columns predict the third one, a multi-directional model, such as MERCS, looks like this. And the key thing is that for each attribute of your dataset, there's at least one component model of the ensemble that predicts exactly that attribute. And concretely, MERCS uses decision trees. So in this case, you have 3 decision trees. Decision tree 1 predicts the last column, decision tree 3 predicts the first column, decision tree 2 predicts the second column. And a more compact representation, it looks like this, where each row basically depicts the prediction task that this decision tree was trained for. Now the problem is that there can be a discrepancy between the models that you have in your MERCS model, between the decision trees in your MERCS model, and the actual prediction tasks that the user asks you to solve. So that's this being robust to missing values at prediction time. So the perfect tree might not exist. For example, here query 2 is from attribute 3 predict attribute 2, or from the last column predict the middle column. You don't have a single decision tree that actually solves that task. So this discrepancy is what the prediction algorithms in MERCS must solve. To do this, we rely on 2 main IDs, attribute importance and chaining. I'll start with attribute importance. So the question is just which trees do I use? And the assumption is, well, trees with many missing input attributes are likely to be mistaken. And the idea is that attribute importance can just quantify this in a neat way. So just to give you an idea, this is the definition. So attribute importance, given an attribute in a decision tree, looks like this. It's a sum over all the splits where this attribute is used. So all the splits that use this attribute, you sum the information gain of that split, and this is a weight that weights each term, and it basically means that splits that occur higher in the tree, so closer to the root node, count more because they have effect on more instances. And then our criterion is basically a sum of those attribute importances. But so sum over what? Well, we sum the attribute importances of each attribute that occurs both as an input of the decision tree and as an input of the prediction task given to us by the user. So if this quantity equals 1, that means that your decision tree is completely appropriate to use given the query provided to you by the user. If this quantity equals 0, then that means that your tree is completely unapplicable. So a concrete example, the baseline case would be, given this query, from attribute 1 and 3 predict attribute 4, just use all decision trees in your ensemble, in your MERCS model that predict attribute 4. But here you can already see that using decision tree number 1 would be a pretty dumb thing to do, since its only input attribute is missing. So it's basically acting on no information at all. So what our strategy, the most relevant attribute importance prediction strategy, does is that it tells you which trees you can actually use best. So in this case, it would select decision tree 2, since its most important attribute, attribute 1 here, is actually given, and its least important input attribute is missing, but still it's the best tree to use in this case. So that's what this attribute importance gets you. Secondly, chaining, again, the same problem. But so now the idea or the assumption would be that your missing inputs are actually also predictable with the MERCS model itself, because after all, it is a multi-directional model. So in a sense, we're going to chain component trees, as in outputs of one tree will become the input of another tree to answer a given query. There's 2 ways to do this. I'm only going to talk about the bottom-up way in this presentation. So concretely, it looks like this, given a query. So from attribute 1 and 2, predict attribute 3. So the query looks like this. And here I depict the state of knowledge of my dataset. So here my first 2 columns are known, my last 2 columns are unknown. And what you're going to do is apply the MRAI strategy over and over again. So concretely, use the most appropriate models given attribute 1 and attribute 2. So that would mean these 2 guys. And they both predict attribute 4. So your state of knowledge changes to this, and then you just repeat. So then you use the most appropriate models given A1, A2, and A4. So you just consider A4 a given or a known attribute now. That selects these 2 guys, and they actually predict attribute 3. So this one here, which was actually the one that you originally cared about. And then the algorithm terminates. So the chaining is that these 2 guys actually helped the guys that came after them in the chain to arrive at their prediction. What you get from this is more robustness to missing values. So on the x-axis, you see always more missing input attributes. And then you see that the green line, the baseline, actually drops in performance quite sharply. The red line, which is the bottom-up chaining strategy, drops way more slowly. So where the green line is at 20% of missing attributes, the red line only arrives at that point around 40 or 50% of missing attributes. The black line here is the most robust one. That's a probabilistic graphical model. So the question becomes, why not use this always? Well, this graph should answer that. This is the relative speedup versus a probabilistic graphical model. MERCS models are decision trees, so they're really fast at prediction time. So at least we're around, well, if we again look at the red symbol, which is the bottom-up chaining, we're around 1 order of magnitude speedup, sometimes around 3 orders of magnitude of speedup. So that's pretty nice. So in conclusion, can we make a MERCS model robust to missing values at prediction time? The answer is yes, if you use chaining and attribute importance. This brings us to our second research question: how does MERC compare against MissForest, which is a well-established tree-based technique to deal with missing data? So first, let me explain a bit about MissForest. This is also a multi-directional model. So you train a model and you predict your missing values. So this is your initial state, and then you predict these missing values like this. But then, crucially, it's an iterative procedure. So what you then do is that you retrain your model, taking this data along with the fixed missing values as your input data, and again you predict them until you converge, like until there's no more difference between subsequent iterations. So this works very well, but it's just not so adequate for our current problem setting, so the missing values at prediction time setting, because of the following reasons. So you have your training data and then your test data, your queries that come in one by one. And as you can see here, you need to be robust to missing data at prediction time, because sometimes test queries, where you need to predict the last column, still have missing data in their input columns. So to do this with MissForest, you actually would need to do something along these lines. So you take your training data, and then this instance comes in as a query. You need to take this instance and the training data. You need to make this dataset, which has missing values here and here. You need to run the MissForest algorithm to eventually get a prediction for this value right here, which is the one you care about. And you need to do this, well, this is crucial, you need to do this for every test instance that comes in, because they don't come in at the same time. So again, you need to take your training data, extend it with one row of your test instance, and then you need to run the MissForest algorithm to finally get a prediction right here. MERCS is much more appropriate for this setting. Takes in the training data once, the MERCS algorithm gives you a MERCS model, and as we explained before, this MERCS model is actually robust to missing values at prediction time, as in your test instances come in one by one. For instance, take the second one, given attribute 1, predict the last column, and the MERCS model can just deal with this. So it will give you a prediction for the last column, even though this attribute might be missing, and MERCS model can do this for each of the query instances. So what does this get you? Well, first, in terms of predictive performance, here you see a win-draw-loss comparison. In the overwhelming majority of cases across data sets, you see that this graph is mostly blue, which means in most cases there's absolutely no difference between using MERCS or MissForest. In some data sets, MissForest wins, but in other data sets, MERCS wins more. So in terms of predictive performance in this setting, you won't really notice the difference. That's the takeaway message. However, in terms of time costs involved, you will notice the difference, since MissForest needs to retrain all the time in order to generate its predictions, which MERCS does not. And the MERCS prediction algorithms are pretty efficient. So we are around 2 orders of magnitude of speedup, which is of course a very nice thing to have. So ultimately, well, how does MERCS compare to MissForest? Well, MERCS performs at par for a fraction of the time cost in this setting, which is a pretty nice result. And so to summarize everything, can MERCS be made robust to missing values at prediction time? Well, yes, if you use this chaining and attribute importance. How does it compare to MissForest? Well, it compares pretty well. Same performance for a fraction of the time cost in this particular setting. This concludes my presentation. Thank you for your attention. If you're curious, you can check out our GitHub.